Welcome to Understand All. I'm your host, Aslakir Gareleaf, and today we're embarking on a mind-bending journey into the realm of quantum entanglement. Buckle up, because we're about to explore one of the most bizarre and fascinating phenomena in the universe. Imagine two particles, separated by vast distances, yet somehow intimately connected. What happens to one particle instantly affects the other, no matter how far apart they are. It's like a cosmic dance, choreographed by the strange laws of quantum mechanics. This peculiar phenomenon, known as quantum entanglement, has baffled scientists for decades. Even the great Albert Einstein was skeptical, famously calling it spooky action at a distance in a 1935 paper co-authored with Boris Podolsky and Nathan Rosen, known as the EPR paper. But as we'll see, experiments have proven that entanglement is very real, and it's opening up a world of possibilities in fields like quantum computing and cryptography. So, what exactly is quantum entanglement? In simple terms, it's a connection between two or more particles that persists no matter how far apart they are. When particles become entangled, their quantum states are linked, and measuring one particle instantly determines the state of the other, even if they're light years apart. It's like having a pair of magic dice. Roll one die, and the other will always show the opposite face, instantly, no matter how far apart they are. But here's the kicker. Unlike regular dice, the outcome isn't determined until you actually make the measurement. Before that, the particles exist in a superposition of all possible states. This mind-bending concept challenged the very foundations of physics. How could particles communicate faster than the speed of light? Einstein argued that there must be some hidden variables, some unseen factors that predetermine the outcomes. But in 1964, physicist John Bell proposed a way to test this idea, now known as Bell's theorem. Bell's theorem provided a mathematical framework for testing the predictions of quantum mechanics against those of local hidden variable theories. If quantum mechanics was correct, then entangled particles would behave in a way that couldn't be explained by any local hidden variable theory. The first experimental verification of Bell's inequalities came in 1982, when physicist Alain Aspect and his team conducted a series of groundbreaking experiments. They found that entangled photons, separated by 12 meters, behaved exactly as quantum mechanics predicted, violating Bell's inequalities and ruling out local hidden variable theories. Aspect's work provided compelling evidence for the reality of quantum entanglement. Since then, scientists have pushed the boundaries of entanglement even further. In 2017, a team of Chinese researchers achieved quantum entanglement over a record-breaking distance of 1,200 kilometers using the Michius satellite. This feat, reported in the journal Science, demonstrated the feasibility of a global quantum communication network. But entanglement isn't just a curiosity of the quantum world. It has real-world applications that could revolutionize computing and communication. In quantum cryptography, entangled particles are used to create unbreakable encryption keys. If an eavesdropper tries to intercept the key, the very act of measuring the particles will disturb their entanglement, alerting the communicating parties to the breach. Quantum computing, too, relies on entanglement to perform complex calculations. While classical bits can only be in one state at a time, 0 or 1, quantum bits, or qubits, can exist in multiple states simultaneously, thanks to superposition. When qubits are entangled, they can perform certain computations exponentially faster than classical computers. In fact, Google claimed to have achieved quantum supremacy in 2019 using a 53-qubit processor to perform a calculation in 200 seconds that would take a classical supercomputer 10,000 years, according to their paper in Nature. But the implications of entanglement go beyond practical applications. They strike at the heart of our understanding of reality itself. Entanglement seems to defy our intuitive notions of locality and causality. How can two particles be so intimately linked, even when they're separated by vast distances? Some physicists, like the late David Bohm, have proposed that entanglement hints at a deeper level of reality, where everything is ultimately interconnected. Others, like Nobel laureate Frank Wilczek, see entanglement as a fundamental feature of quantum reality, as essential as space and time. There's still much we don't understand about entanglement. How does it scale to larger systems? What role does it play in the universe at large? Could it be involved in the workings of consciousness itself? These are open questions that researchers are actively exploring. One intriguing area of research is the role of entanglement in biology. Some studies suggest that quantum effects, including entanglement, may be involved in processes like photosynthesis and avian navigation. A 2020 paper in the journal Science Advances reported evidence of quantum entanglement in the photosynthetic complexes of green sulfur bacteria, hinting at a functional role for entanglement in living systems. Another frontier is the quest to build a quantum internet, a network of entangled nodes that could transmit quantum information over vast distances. Such a network could enable secure communication, distributed quantum computing, and even teleportation of quantum states. While still in its early stages, the quantum internet is an active area of research, with initiatives like the European Quantum Internet Alliance working to make it a reality. As we continue to probe the mysteries of entanglement, we may find that it reshapes our understanding of the universe in profound ways. It challenges our classical intuitions and invites us to embrace a world where the boundaries between the microscopic and the macroscopic, the local and the non-local, begin to blur. So the next time you hear about spooky action at a distance, remember, it's not just a quirk of quantum theory. It's a window into the fundamental fabric of reality, a glimpse of the strange and beautiful dance that underlies everything from the subatomic to the cosmic. And that, my friends, is the fascinating world of quantum entanglement. As the great Richard Feynman once said, if you think you understand quantum mechanics, you don't understand quantum mechanics. But perhaps, by embracing the weirdness and wonder of phenomena like entanglement, we can come a little closer to grasping the true nature of the quantum world. And that's a wrap for today's episode. I hope you enjoyed our exploration of quantum entanglement and gained valuable insights along the way. Remember to tune in next time for more captivating knowledge. Until then, stay curious and keep exploring the wonders of the world around you.